So let's kick things off by reviewing quadratics. A quadratic is a second degree expression, or one that has a variable with a power of 2. So ax squared plus bx plus c is equal to 0 is the standard form of a quadratic equation. The leading coefficient of our quadratic term cannot be equal to 0. Otherwise, x squared would not exist. 0 times anything would be 0. And thus we would not have a variable with an exponent of 2. So a cannot be equal to 0. B can be equal to 0. So you can have a quadratic that just has one variable, and that variable has an exponent of 2. And you'll notice here how we've written this expression. We have the term with the largest exponent further to the left. This variable has an exponent of 1, and this term does not have a variable. So you'll see the standard form of a polynomial has the terms with the highest degrees furthest to the left. So for example, if we had 3x squared minus 4x plus 7 is equal to 0, this is the standard form of the polynomial. We have a degree of 2, a degree of 1, and a degree of 0. But if we move the quadratic to the middle of our expression, such as this example, this would no longer be in standard form. 6x minus 5x squared minus 2 is equal to 0 is not standard form of the polynomial. In order for this to be in standard form, negative 5x squared would need to be furthest to the left. And now this equation is in standard form. The reason I bring this up, throughout this chapter we will be dealing with quadratics, and when you see them they will be in standard form. This is just the way in which we usually write out these expressions to keep things consistent. Now, the solutions of a quadratic equation, also known as the roots or zeros, are the x values where the function is equal to 0. So for example, this parabola that represents a quadratic equation has a solution here. So there's one x value where the function has a value of 0. For this function or parabola, we see that it has two solutions. And for this one, we see that it does not cross our x-axis, so this one has 0 solutions. Now, why is this important? The reason why you are factoring quadratics specifically is because throughout algebra, you are trying different ways to figure out the values where the function crosses this x-axis. So this is why factoring polynomials, specifically quadratics, comes up very frequently throughout your algebra chapters. We won't be solving the quadratics in this chapter, we'll just be focusing on factoring them, but I wanted to make sure that you understood why you needed to know how to factor polynomials, specifically quadratics. Now, in order to understand how you find these solutions, we must review the zero product property. The zero product property states that if the quadratic is equal to 0, then either one or both of the factors are equal to 0. So let's say you had some quadratic expression and it's equal to 0, and you wanted to factor this expression. When you do so, you would have one factor times another factor, and we know that the product is equal to 0. So by knowing that one or both of the factors must be equal to 0, in order to solve for x, or to find the solution or solutions, we set each factor equal to 0 and solve for x. So one of the factors, x minus d, we set that equal to 0 and solve for x. To do so, we add d to both sides, giving us x is equal to some number d. So that would be one solution. And another potential solution we find by doing x minus e is equal to 0. So we add e to both sides, giving us x is equal to some number e. So this is how you would go about using the zero product property to find the solutions or the x values where the function crosses the x-axis. So this is why we want to go about factoring quadratics specifically. Now, let's discuss factors. The factors of a product are the numbers and variables that can be multiplied to get the product. So let's say we had the number 20. You can get to 20 by multiplying 1 times 20. So these are both factors. You can get to 20 by multiplying 2 times 10. So these are both factors. And you can get to 20 by multiplying 4 times 5. So these are both factors as well. So these are the numbers that you can multiply to get to 20. So all 6 of these numbers are factors of 20. Now let's say you had a term that had both numbers and variables. Negative 15 x squared y to the fifth is a product because you are multiplying negative 15 times x squared and multiplying these times y to the fifth. Right? So it's a result of multiplication, so it's our product, which lets us know that the individual pieces of that product are our factors. So the factors of negative 15 x squared y to the fifth are negative 15, x squared, and y to the fifth. Now that is for a monomial. For polynomials, you can get the factors several different ways. In this case, we have factors 4x being multiplied times the binomial negative 3x squared y plus 5, and that would give you a product of negative 12x cubed y plus 20x. You can also get a trinomial that has the variable twice, x squared plus 2x minus 3, and the factors of that polynomial would be x plus 3 times x minus 1. So again, we would multiply these two terms, making those our factors, and we get this expression as a result, making it our product. So there will be several different types of products that we will run into throughout the remainder of this chapter, and we'll discuss how we go about finding the factors for said product or expression more specifically. Now let's move on to discuss the greatest common factor. To do so, we must first review the factor tree. A factor tree is a diagram used to determine the prime factors of a positive number. So let's say we had the positive number 40, and we wanted to determine the factors of 40. We want to break 40 down until we have all of the prime factors of 40, the factors that cannot be broken down any further. So we have 2 times 20 would give us 40. 2 is a prime number. 20 is not. So we'll try to break up 20 further. 20 can be broken up into 2 times 10. 2 is a prime factor, so that's ideal. 10 can be broken up further into the product of 2 times 5, both of which are prime numbers. So since we have prime factors at the bottom of this tree now, it cannot be factored any further, which lets you know this prime factor tree is done. And you'll notice that you'll be able to multiply the prime factors to get the original number. 2 times 2 is 4. 4 times 2 is 8. 8 times 5 is 40. Let's say we had a different number, 120. Let's take a look at the factor tree for this number. Since it is an even number, we can split it in half, giving us 2 times 60. 2 is a prime factor, so we can leave that side. So we'll take a look at 60. 60 can be broken up into 2 times 30. 2 is a prime factor, so we'll leave that side. We'll break up 30 into the product of 2 times 15. 2 is a prime factor, so we'll leave that side. 15 is not, so we'll break that down further into the product of 3 times 5. And now we have prime factors at the end of our tree. And we see 2 times 2 is 4. 4 times 2 is 8. 8 times 3 is 24. And 24 times 5 is 120. So we have factored 120 as far as we can. Now if we have two numbers, 40 and 120, you'll notice that since they're both even, we were able to start breaking those numbers down by dividing them by 2. And if you have an odd number, you want to try dividing it by an odd prime number, such as 3, 5, or 7 to start. So for example, here we had 15. 15 can be divided by 3. That would give us 3 times 5. So that is how you break down a number to get its prime factors. Now let's discuss how you would go about finding the greatest common factor between two numbers. Now, the greatest common factor is the largest number that can divide two numbers. It's a common factor, and it's the greatest or the largest one. So let's take 40 and 120, for example. Let's say you're asked to find the greatest common factor and check the answer for 120 and 40. So you start step 1 by creating a prime factor tree for each number. They're both even numbers, so you can start by dividing them both by 2. 120 is equal to 2 times 60. 60 is equal to 2 times 30. 30 is equal to 2 times 15. 15 is equal to 3 times 5. For 40, we have 40 is equal to 2 times 20. 20 is equal to 2 times 10. And 10 is equal to 2 times 5. So once you create a prime factor tree for each number, the next thing you want to do, step 2, is circle each prime number that is common to both factor trees. So we have 3 2's that are common to each factor tree. We do not circle this 3 since this factor tree does not have a 3. And we circle this 5 since this factor tree also has a 5. And now that you've circled each prime factor that is common to both, the third step is to multiply these numbers in one of the factor trees. You don't need to multiply it twice. Multiply the prime factor circled in one of the trees to find the greatest common factor. So the greatest common factor is going to be equal to 2 times 2 times 2 times 5. 2 times 2 is 4. 4 times 2 is 8. 8 times 5 is 40. So the greatest common factor between 120 and 40 is equal to 40. Now to check this answer, we want to divide both of the original numbers by the greatest common factor, because if you divide a number by a factor, you should get an integer value. You should not get a decimal. When we divide 120 by 40, we get 3. And when we divide 40 by 40, we get 1. So we get integer values for both. So this helps us confirm that we did find the greatest common factor. So those are the steps you would take to find the greatest common factor of two numbers. Let's now have you complete a few practice questions. Question number 1. Find the greatest common factor of 65 and 15. Question number 2, find the greatest common factor of 72 and 16. In question number 3, find the greatest common factor of 180. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, you were asked to find the greatest common factor of 65 and 15. Step 1, create a prime factor tree for each number. 65 can be divided by 5. 5 times 13 gives you 65. 5 is a prime factor and 13 is a prime factor as well. So this is the prime factor tree of 65. 15 is divisible by 3. 3 times 5 gives you 15. So this is the prime factor tree of 15. Now the second step, you want to circle each prime number that is common to both factor trees. And in this case, that is just the number 5. 13 is not a factor of 15. And 3 is not a factor of 65. Now that we've done that, we are done. Normally we would multiply the numbers that are circled in the prime factor tree, but we just have one number circled in each, so that is our greatest common factor. And we can check this answer by dividing the original numbers, 65 and 15, by the answer, 5. to make sure that we get an integer value. 65 divided by 5 is equal to 13. 15 divided by 5 is equal to 3, thus confirming that our greatest common factor of 65 and 15 is equal to 5. Question number 2. You are asked to find the greatest common factor of 72 and 16. So step 1, create a prime factor tree for each number. 72 is an even number, so we start by dividing it by 2, giving us 2 times 36. 36 is an even number, so we divide it by 2, giving us 2 times 18. 18 is an even number, so we divide it by 2, giving us 2 times 9. 9 is an odd number, so we consider dividing it by 3 first, and it can be divided by 3, giving us 3 times 3. And now that we have all prime factors at the end of our tree, this prime factor tree is completed. Let's take a look at 16. 16 is an even number, so it can be divided by 2, giving us 2 times 8. 8 is an even number, so it can be divided by 2, giving us 2 times 4. And 4 is an even number, so it can be divided by 2, giving us 2 times 2. And now that we have all prime factors at the end of our tree, this prime factor tree is now completed as well. So the second step is to circle each prime number that is common to both factor trees. And we'll see that each prime factor tree has a total of 1, 2, 3 2s. We do not circle this 2 because this tree does not have a fourth 2. And we do not circle either of these 3s because this factor tree does not have a single 3. So these 3 2s are the only numbers that are common to both factor trees. And now the third step, we'll find the greatest common factor by multiplying the numbers that are circled, giving us the greatest common factor is equal to 2 times 2 times 2, which would be equal to 8. And now that we found the greatest common factor, we want to check the answer by dividing the original numbers, 72 and 16, by the answer, 8, to make sure that we get integer values when we do so. 72 divided by 8 is equal to 9, so that works. And 16 divided by 8 is equal to 2, so that works. Thus confirming that the greatest common factor of 72 and 16 is equal to 8. And now question number 3. You are asked to find the greatest common factor of 180. Step 1, create a prime factor tree for each number. 100 is even, so we can start by dividing it by 2, giving you 2 times 50. 50 is even, so you can start by dividing it by 2, giving you 2 times 25. 25 is odd, so you want to start by trying to divide it by 3, which you cannot. Then you try dividing it by 5, which you can, giving you 5 times 5. We have all prime factors now at the end of our tree, so that one is done. For 80, we have 2 times 40. 40 is even, so you can divide it by 2, giving you 2 times 20. 20 is even, so you can start by dividing it by 2, giving you 2 times 10. 10 is even, so you can divide it by 2, giving you 2 times 5. And now we've completed this factor tree as well. So now we can find the greatest common factor by circling each prime number that is common to both factor trees, and then by multiplying those numbers that are circled, giving us the greatest common factor is equal to 2 times 2 times 5, which would be 2 times 2, which is 4. 4 times 5 would be equal to 20. So the greatest common factor between 100 and 80 is equal to 20. And now to check the answer, we want to divide both 100 and 80 by 20 to make sure that we get whole numbers as our quotient. 100 divided by 20 is equal to 5, so that works. 80 divided by 20 is equal to 4, so that works. So the greatest common factor of 180 is equal to 20.